Hello guys, welcome to our presentation. Our topics include the properties of alpha, beta and gamma rays and also the Soddy Fajans displacement law. Now let me introduce the presenters. The presenters are Arunima P S, Julin George, Kripal S, Sree Lakshmi and Maria Paul. We are second year mathematics students of SH College. Before beginning the presentation, we would like to sincerely thank Dr. Pius Augustine, our mentor, who gave us the opportunity to do a presentation. Thank you, Pius, for giving us the courage and platform to enhance our skill. Even though our topic begins with the properties of alpha rays, let us have a quick recap on what is radioactivity and the history behind it. As you all know, radioactivity is a process of spontaneous decay and transformation of unstable atomic nuclei to form more energetically stable atomic nuclei, and it is accompanied by the emission of radiation. We should also note that radioactivity is a random process at the level of single atom. Therefore, it is an attribute of individual atomic nuclei. Then, radioactivity can also be referred to as radioactive decay, nuclear decay, radioactive disintegration or nuclear disintegration. Are you aware that the discoveries of X-rays and radioactivity happened in back-to-back years? Better still, it was the discovery of X-rays that actually led to the discovery of radioactivity. The modern understanding of ionizing radiation got its start in 1895 with William Röntgen's discovery of X-rays. Then the phenomenon of radioactivity was first discovered by Henry Becquerel in 1896. Becquerel wondered if there was a connection between the newly discovered X-rays and the phosphorescence he was investigating, because he thought that any substance that fluoresced intensely might also emit X-rays. It happened that he had previously worked with a substance that fluoresced strongly when exposed to sunlight. So he was thinking that if it might also be emitting X-rays which was previously undetected. Thinking that X-rays might be related to fluorescence and phosphorescence, processes in which substances absorb and emit energy as light, Becquerel stored some photographic plates and uranium salts in a drawer. Expecting to find the plates only lightly fogged, he developed them, but he was surprised to find the sharp images of the salt. Though originally thinking that the rays were given off by phosphorescent uranium salt after prolonged exposure to sun, he eventually abandoned this hypothesis. Through further experimentation, including non-phosphorescent uranium, he instead came to recognize that it was the material itself that gave off the rays. Becquerel named these rays Becquerel rays, when he went on to announce that this radiation was in fact a property of the uranium atom. Radioactivity was born. Becquerel also showed that uranium salt emitted a penetrating radiation independent of external influences. He also demonstrated that this radiation could discharge electrified bodies. Although it was Henry Becquerel that discovered the phenomenon in 1896, it was his doctoral student Marie Curie who named it radioactivity in 1898. She would go on to do much more pioneering work with radioactive materials, including the discovery of additional radioactive elements polonium and radium. Then again in 1898, Paul Villard discovers gamma rays, but he didn't name it gamma rays. It was actually Rutherford who named it gamma rays in 1900. Rutherford, who worked as a student with J.J. Thomson, had carefully studied the absorption of Becquerel rays, and he found that one component, which he called the alpha rays, could be absorbed by a sheet of writing paper or a few centimeters of air. In fact, Becquerel had not detected these alphas because they were absorbed by a box containing the film. The second component, which he called the beta rays, was found to be 100 times more penetrating. He published this result in 1899.
Rutherford's experiment. The existence of three types of radiation is demonstrated by the following simple experiment. A small quantity of radium R is placed at the bottom of a small hole drilled in a lead block. A fairly parallel beam of radiation from R will issue through the hole. This lead block is placed inside an evacuated chamber to avoid absorption of the rays. A photographic plate P is placed at a short distance above the lead block to receive the rays. A strong magnetic field is applied at right angle to the plane of the figure and directed away from the reader. After a fairly long exposure, the photographic plate is developed. Three distance lines will be found on the photographic plate. The alpha particle will be deflected towards the left, indicating they are positively charged. The beta particle will be deflected towards the right, showing they are negatively charged. The gamma rays are not deflected and hit the plate straight. This shows the gamma rays are uncharged or neutral rays. If an electrostatic field is applied in the place of magnetic field, the beta ray will be deflected towards the positive plate, the alpha rays towards the negative, and the gamma rays do not bend at all. Nuclear reactions. Nuclear reactions are processes in which one or more nuclides are produced from the collision between two atomic nuclei or one atomic nucleus and a subatomic particle. The nuclides produced from nuclear reactions are different from the reacting nuclei. The bombarding particle may be alpha particle and a gamma rays photon, a neutron, a proton, or a heavy ion. In any case, the bombarding particle must have enough energy to approach the positively charged nucleus to within the range of the strong nuclear force. Natural radioactivity. Radioactivity is a natural phenomenon that has existed since the origin of Earth. It is present everywhere, in the water, the air, the soil, and the biota. The human being itself is radioactive. There are two types of radioactivity, natural radioactivity and artificial radioactivity, also known as induced or man-made radioactivity respectively. The phenomenon of spontaneous emission of highly penetrating radiation from heavy elements of atomic weight greater than about 206 occurring in nature is called natural radioactivity. Natural radioactivity originates from various sources such as radioactivity element contained in the soil, cosmic radiation that comes from the space and the sun in particular, and the radioactive element that we absorb by breathing and nourishing ourselves. Induced radioactivity, also called artificial radioactivity or man-made radioactivity, is the process of using radiation to make a previously stable material radioactive. The husband and wife team of Irene Juliet Curie and Frederick Juliet Curie discovered induced radioactivity in 1934, and they shared the 1935 Nobel Prize in Chemistry for this discovery. This slide shows the various sources of radioactive elements.
Now we are going to discuss alpha particle, its properties and the uses. Alpha particles are discovered by Ernest Rutherford. Alpha rays are positively charged particles. They are a highly active and energetic helium atom that contains two neutrons and two protons. Most of the alpha emitters occur naturally in the environment. Now we are moving to the properties of alpha particles. The first property is that alpha particle is a helium nucleus with positive charge of 3.2 into 10 raised to minus 19 coulomb, which is equal to 2 times that of a proton star, and a mass of 6.644 into 10 raised to minus 27 kg, which is 4 times that of the mass of a proton. The next property, alpha particles are deflected in electric and magnetic field. As the alpha particles are charged particles, they get deflected in electric and magnetic field, and the direction in which they get deflected indicates that they are positively charged. The next property is about the velocity of alpha particles. The velocity of alpha particles is much less than the velocity of light. The velocity of the alpha particles depends upon the radioactive substances, so different substances has different velocities. The next property is about the range of alpha particles. The range of alpha particles depends upon the type of radioactive substance, their nature, and the pressure of the medium through which they passes. Depending upon these factors, the range of alpha particles give on. The next is another important property, that is about their penetrating power. Alpha
properties of beta particles. As we discussed, beta particle is similar to that of an electron, so their charge is about 1.602 into 10 raised to minus 19 coulomb. And the next is, the beta particles are deflected by electric and magnetic field, and the direction of the deflection shows that they are negatively charged. Their deflection is much larger than the deflection of alpha particle. This shows that the beta particles are much lighter than the alpha particles. And the next is about the velocity. The velocity of beta particles vary from 1% to 99% of the velocity of light. There is enough variation in the velocities of beta particles emitted by the same radioactive substance. This is why enough dispersion is found in these particles in the electric and magnetic field. And next is about the mass. Since the velocity of beta particle is of the order of velocity of light, their mass increases with increase in their velocity. And the next is the beta particles emitted by the same radioactive substance has a continuous distribution of kinetic energy between 0 and a certain maximum value. And this maximum value is different for different substances. So the range of beta particle is not definite, while the range of alpha particle is definite. And the next is about the penetrating power. The penetrating power of beta particle is about 100 times larger than the penetrating power of alpha particle. That is, they can pass through 1 millimeter thick sheet of aluminium. And next is about the ionizing power. Beta particles ionize gases, but their ionizing power is much smaller, only 1/100th of the ionizing power of alpha particle. As beta particles cannot produce ionization continuously, their tracks in the cloud chamber do not appear to be continuous. And the next is beta particles produce fluorescence. They produce fluorescence in calcium tungstate, barium platinocyanide, and zinc sulfide. And the next is beta particles affect the photographic plate more than do the alpha particle. And next is about the uses of beta rays. And here the first one is medical imaging. Most radioisotopes, chemicals that produce radiation, are used in hospitals as medicines. Beta rays radioisotopes are used to illuminate parts in a patient to avoid the formation of specific tissue in a process called a brachytherapy. And the next is industrial uses. Beta particles have been used abundantly in the industrial processes. Beta rays can pass through industrial materials. And the next is tracers. Chemical and biological researchers use radioisotopes as tracers. And the next is quality control in industries. Beta rays are applicable when the testing thickness of things like paper, aluminium, and plastics from the system of rollers. And the next is the treating conditions. That is, beta radiations is used to treat eye and bone cancer. And the last one is radiation therapy. Small superficial tumors can be treated with the use of beta radiation. Thank you, and next I invite Julin to continue the presentation.
Gamma rays. A gamma ray is a penetrating form of electromagnetic radiation arising from the radioactive decay of atomic nuclei. It consists of the shortest wavelength electromagnetic wave and so imparts the highest photon energy. They are waves arising from the high frequency end of the electromagnetic spectrum and has no mass. Gamma emitting radionuclides are the most widely used radiation sources. While gamma rays penetrate many material, this does not make them radioactive. The three radionuclides that are by far the most useful are cobalt-60, cesium-137, technetium-99m, and americium-241. Properties of gamma rays. Like X-ray, the gamma rays are electromagnetic wave. The energy of gamma photon is very large, of the order of million electron volt. Hence, the wavelength of a gamma photon of energy 1 mega electron volt is 0.01 Armstrong, which is about 1/100th part of the wavelength of X-ray. Gamma rays are not deflected by electric and magnetic field. This indicates that they have no charge. Gamma rays travel with the speed of the light, that is 3 into 10 raised to 8 meter per second. The penetrating power of gamma rays is much more than that of alpha and beta particles. They can pass through 30 centimeter thick iron sheet. Gamma rays ionize gases, but their ionization power is very small compared to that of alpha and beta particles. Gamma rays produce fluorescence. Gamma rays affect photographic plate more than do beta particles. Gamma rays are diffracted by crystals in the same way as X-ray. Though there is much similarity between X-rays and gamma rays, yet their sources of origin are different. X-rays are produced by the transition of electron in an atom from one energy level to another energy level. That is, it is an atomic property. Whereas gamma rays are produced from the nucleus. That is, it is a nuclear property. Gamma rays are absorbed by substances and give rise to the phenomena of pair production. When a gamma photon strikes the nucleus of some atom, its energy is converted into an electron and a positron. Uses of gamma rays. Gamma rays are used both in medical and industrial field. They are used as medical treatment, medical diagnostic, and also in food industry. They are also used as sterilization of medical equipment in hospital, pasteurization of certain foodstuffs, leveling or thickness gauges, industrial radiography, measurement and control of the flow of liquid in industrial process, investigation of subterranean strata, measurement of soil moisture, leveling gauges for packaging, food drugs and other products, etc.
Soddy-Fajans displacement law. The law of radioactive displacement, also known as Soddy and Fajans law in radiochemistry and nuclear physics, is a rule governing the transmutation of elements during radioactive decay. It is named after Frederick Soddy and Casimir Fajans, who independently arrived at it in 1930. The law describes which chemical elements and isotopes is created during the particular type of radioactive decay. During a radioactive disintegration, the nucleus which undergoes disintegration is called a parent nucleus, and that which remains after the disintegration is called a daughter nucleus. These are the photographs showing Casimir Fajans and Frederick Soddy. Soddy-Fajans displacement law. In all known radioactive transformation, either an alpha or a beta particle is emitted by the atom. When a radioactive atom emits an alpha particle, a new atom is formed whose mass number is less by 4 units and atomic number less by 2 units than that of the parent atom. A radioactive atom emits a beta particle. The new atom formed has the same mass number, but the atomic number is increased by 1 unit.
Now let us discuss the radioactive decays in detail. Radioactive decays are a result of the three fundamental forces working in the nucleus: the strong force, the weak force, and the electromagnetic force. In all the cases of radioactive decays, the emission of radiation increases the nucleus stability by adjusting its neutron-proton ratio. The three decays which we are going to discuss mainly here are alpha decay, beta decay, and gamma decay. Please note that beta decay can again be divided into beta plus decay and beta minus decay. In the case of a beta plus decay, and positron is emitted, and in case of beta minus decay, an electron is emitted. Here we are mainly concerned with beta minus decay. Now let us watch a video which gives a better understanding about the alpha and beta decay.
Emit radiation. There are three types of decay: alpha decay, beta decay minus, or beta decay plus. Alpha decay is the loss of an alpha particle. An alpha particle is made of 2 neutrons and 2 protons. They have a mass of 4 and a charge of +2. When an atom loses an alpha particle, the mass number decreases by 4 and the atomic number decreases by 2. A new element is formed that is 2 places lower in the periodic table. When an isotope has too many neutrons, it decays by beta minus decay. A neutron changes into a proton and an electron. The proton is retained by the atom, while the electron is lost. The lost electron is high energy and is called a beta particle. By losing a neutron whilst gaining a proton, the mass number of the atom remains the same, but the atomic number increases by 1. A new element is formed that is 1 place higher in the periodic table. When an isotope has too many protons, it decays by beta plus decay. A proton is converted into a neutron and a positive beta particle called a positron. Positrons have the same mass as electrons, but the opposite charge. By losing a proton but gaining a neutron means the mass number stays the same, but the loss of a proton means the atomic number decreases by 1. So how do we know if an atom is stable or unstable? We can determine whether a radioisotope is likely to decay and what type of decay is likely to occur by looking at its position on a proton-neutron NZ graph. This graph shows the number of protons on the x-axis and the number of neutrons on the y-axis. This is the stability line. If a radioisotope lies left or right of this line, it is unstable and likely to decay to become stable. A radioisotope that lies to the left of the stability line has too many neutrons and is likely to undergo beta minus decay, so give off electrons. A radioisotope that lies to the right of the stability line has too many protons and is likely to undergo beta plus decay, so give off positrons. If particles have a high number of protons, usually more than 82, they are likely to undergo alpha decay. In this video, we have learned that unstable nuclei either have too many protons or too many neutrons, which upsets the strong nuclear force holding the atom together. Unstable nuclei try to balance themselves by giving off the excess proton or neutron either through alpha, beta minus, or beta plus decay.
I hope that everyone understood what is alpha and beta decay from the previous YouTube video. Now, when we summarize, we know that in case of an alpha decay, the unstable atom, when undergoing an alpha decay, changes to a new, more stable atom whose atomic number is less by 2 units and mass number is less by 4 units when compared to the parent atom. That is what is shown in this slide. And in case of a beta emission, there will be no change in the mass number of the daughter nuclei, but the atomic number of the daughter nuclei will be greater than 1 when compared to the atomic number of the parent in case of a beta minus emission. In the case of a gamma decay, there will be no change in the atomic number or the mass number of the daughter nuclei. That is when an atom decay by emitting an alpha or a beta particle to form a new atom, the nuclei of the new atom formed may still have too much energy to be completely stable. These atoms will emit gamma rays to release that energy. Now let us look at some examples. The first example is you have to find Y, and it is shown that thorium is undergoing a beta decay. So as we all know, in the case of a beta minus decay, the atomic number of the daughter will be greater than 1 unit compared to the parent atom. You can see, therefore, you have to add 1 to the atomic number of thorium, that is 90, plus 1, 91, and we get platinum. In the second case, it is you have to find the missing starting element, and we have given that it was alpha decay and the daughter nuclei was lead. So now since we know that in the case of an alpha decay, the atomic number of the daughter will be less by 2 and mass number less by 4. Here we have to reverse it, that is we have to add 4 and add 4 to the mass number and add 2 to the atomic number to find the parent atom, that is 214 plus 4 is 218 and 82 plus 2 is 84. That hence we get the X. And the third question is write the equation for alpha decay of uranium 234. We know that the atomic number of uranium is 92, and hence when it is undergoing an alpha decay, it changes to thorium. These are some more examples. Here the first question is, again you have to find by and it is given it is an alpha. Natural radioactive series. With the help of the displacement law, one can easily determine the mass and atomic number of the different elements in the successive radioactive changes if the mass number and atomic number of the parent atom is known. The different atoms produced at different stages of disintegration will naturally form a series. The first member is called the parent, the intermediate members are called the daughters, and the final stable member is called the end product. Uranium series, actinium series, thorium series, and neptunium series are 4 such series that are known at present, and here neptunium series is the artificial one, whereas uranium series, actinium series and thorium series are naturally produced ones. Each of these series consists of a succession of daughter nuclei or daughter elements which are all derived from a single parent nucleide. Here we can see the mass number, the series, the parent, and half-life, and the stable end product. The thorium series or the foreign series begins with thorium 232 90, and it has a half-life of 1.39 into 10 raised to 10 years, and its stable end product is lead. Then again foreign plus 1 series is headed by neptunium, and its parent is also neptunium, and it has an half-life of 2.25 into 10 to the power 6 years, and its stable end product is bismuth. And foreign plus 2 is the uranium series, and it is headed by uranium 238 and has a half-life of 4.51 into 10 to the power 9 years, and its stable end product is lead 206. And the 4n plus 3 series or the actinium series is headed by uranium 235 and has an half-life of 7.07 into 10 raised to 8 years, and its stable end product is lead 207. Now, why are there exactly 4 natural radioactive series? We know that the alpha decay reduces the mass number of a nucleus by 4. Thus, the nucleides whose mass number are all given by A is equal to 4, and where n is an integer can decay into one another in descending order of the mass number. All the radioactive nucleides whose mass number obey the equation A is equal to 4n are thus said to be the members of 4n series. Radioactive nucleides whose mass number obeys the equation 4n plus 1 is equal to A belongs to 4n plus 1 series, and similarly the radioactive nucleides whose mass number satisfies the equation A is equal to 4n plus 2 and A is equal to 4n plus 3 belongs to 4n plus 2 series and 4n plus 3 series respectively. Thank you. That is the end of the presentation. Hope you guys understood what he said. Thank you.